It's now winter, so I hope you're ready for that. I have my ski passes ready, so yeah, I'm ready to go. The season passes. Anyways, hopefully we're feeling good about homework, and if you're not feeling so good about homework, I'll be around for after class day. I can answer questions due tomorrow. And if you have any questions about projects, general questions, I'm happy to take them right now, or if you want to talk specifics, I can do that after class today as well. We're gonna do part 2 on transformers today. We spent a bunch of time talking about like the parts of the architecture, just what they are, kind of how certain aspects of like sequential modeling kind of fit into this interesting sort of set to set kind of architecture, and just kind of went through the calculations for what self-attention looks like. This interesting idea that in every layer you're projecting the input tokens to these queries, these keys, these values, and then using all of that information to create new tokens that has the possibility of in general of kind of mixing all the information from each of the tokens, all of those representations, whatever layer you're at, to create the representation, the output representation for that particular token, and not just kind of however many layers of that you have, you just kind of keep going, and then you say, well, there's our representation at the end of that sequence of layers.
Would you need those representations?
Say it louder, sorry.
So each representation from like the encoder layer, would you feed that output into the encoder, or just the end?
Yeah, so when we have the particular encoder-decoder formulation of the transformer, which is like the original formulation, then yeah, there was, if you remember, actually, let me just go straight to it. We talked about this. If you remember, in the decoder layers, there were these arrows that, what this is trying to show is that, each token, so you have however many tokens, 1, 2, 3, each of the tokens that were here, you're going to have some new, token representing. So you have 3 tokens again. They'll look differently because you've learned a whole bunch of stuff along the way here that's changed that representation. And then how does the decoder, get conditioned on those? They get conditioned through this right here, and through this multi-head attention here. And the way that happens is, where in the typical self-attention, where the values and the keys and the queries all come from just the inputs into that head. Here, the values and the keys come from the encoded tokens, and then the queries come from the decoding tokens.
And when you have multiple layers, so you have
you do this conditioning every time.
Okay.
Yeah. Good. Good question. Yeah.
What's the thought on that?
Say it loud, because for some reason I don't know if it's the heater or something, but.
Sure. So.
And I'm just an old guy, I can't hear.
A little just follow up on that.
Yeah.
So with the values, keys, queries, and you have these weights that kind of are used, multiply them by the inputs. Does it naturally just kind of happen that they become values, keys, and queries, or are you kind of initializing it in a certain way where?
Yeah, I mean the way that you get values, keys, and queries, remember, is that at every layer you are learning a matrix of weights, a weight matrix, and you're literally just multiplying it. So you take that. So for each token, you take that representation at that layer, and you multiply it by the values matrix, and that will give you the value for that token. Then you multiply it by the keys weight matrix, and that will give you the key associated with that token. And then you do the same thing with the query. There's three different weight matrices that you're learning. Those are the parameters you're learning in that layer. And then that triple of weight matrices for each head.
Same. So let's say for the value, the
Yeah, so like the same token is used, but you get a different value vector, key vector, and query vector because these are different matrices.
If I understand, I think that's like what guarantees that they end up as the like what guarantees a different weight from it, and is it just because
Like
it's
what?
not randomly initialized?
Oh, okay, that's the question. Is that so? Meaning like just why would the weight matrices associated with values, keys, and queries at any layer be different?
I guess I know the queries is like treated a little bit differently, but the values and keys, they both have inputs have the same input,
Yeah.
and they're multiplied by a weight that's created
Yeah.
by the program. So like, how does it know to create?
Yeah. Okay. Yeah. So I mean, this thing that was brought up about like there being, some random initialization, of the weights. Yeah, that could encourage it. But the real answer to this is the answer it's always been for any network we've looked at. These are learnable parameters, and if it can perform the task better by having these matrices, the weights in these matrices be different, then it will do that, right? Like that's the whole point of backpropagation to give us gradients and then doing gradient descent, is that we have an objective, we have a way of basically attributing the error that we're making. Like that objective is usually thought of as like the error that we're making. If there is any error, backpropagation is essentially a way of attributing to all of the weights throughout the whole network, whether that's a couple of weights or hundreds of billions of weights. It's a way of attributing, how much error, how much of the error, is this weight responsible for, and then it will change it, when you take that gradient step. And if it can do better at the task, if it can reduce the loss, by having these things be different, then it will. And of course, that's what ends up happening. There's not like a guarantee that that's going to happen like a priori, like there's something, I don't know, like in the math that has to be that way. It's just that it's going to be that way because let me just step back and say, because there ends up being like lots and lots of parameters, right? Like we'll talk about GPT-3 today, 175 billion parameters, right? These are massive networks. That really, like, what that translates to, if you remember, like this, we think of that as somehow being roughly, like proportional to the capacity to learn stuff. And you can only learn stuff if you have a whole lot of data in which to like learn stuff. And so if you take these high capacity models and then just like learn on a little tiny data set, like maybe these will all be redundant in some way because maybe like there's just not enough signal there to change them. So like in general, the answer to your question is everything I said plus a whole bunch of like information-rich data, data to train it on. I don't know. That's just me kind of spitballing right there for a little bit. Yeah, Chris.
You kind of got close to answering it. Going asking the question the other direction, for like regression, it's possible to construct a data set that like encourages like a lower rank approximation of maybe whatever regression you're doing. So
Yeah.
maybe or whatever.
Yep.
Is it possible to engineer data sets to encourage a behavior, for example, where the values and keys end up being the same? Like it's not really ranked in the same way that regression, but
you don't really think about it as the data set. You think you like if you were to, the way you'd approach that is maybe more. Well, you think about the task and like the objective, but like. Yeah. I mean, I wouldn't know how you would do that, like, because we're talking about really complex interactions between, all of the operations and therefore the weight through all these layers. And again, there's this other result that we're not really focusing on in this class, but I kind of mentioned, which is people have swapped out these attention modules for like less complex operations, but that still do this kind of mixing of the signal across all the tokens. And in certain situations, it basically performs the same as if you had these attention mechanisms. So like, the thing that really matters, it seems, is you just have a sufficient mixing mechanism. So this attention thing is one of those ways of doing it, and it's just, its way of doing it is saying, I'm going to create this mixture, this linear combination of, all these tokens by, just doing these things, like saying, from this token, I want to turn it into something I want to query with. And it's just, again, it's an analogy that kind of like fits with a particular task, but it's not like it fits with all the tasks that this is being used for, right? But like I have this query then gets compared to these keys. Like, the query came from one token, the keys came from all the tokens, and then associated with each of those keys is a value, and then like so the queries and the keys give me my attention weights, some computation of that gives me my attention weights, my values give me the thing that I'm going to combine together in that linear combination, and like that's now like the thing I mix. And it's actually not quite the thing I mix, because if you remember, I have all these heads, then I concatenate that, and I project it one more time, and like that's my thing. And so, and then I do this whole thing where I expand. I do the one more feet forward a layer where I expand and then contract again. So, I mean, these kinds of questions are great, because like you're thinking about like what are the operations, like what do these mean, like why these and not other ones. And again, in all of like deep learning, essentially, the answer is because these work. And that's really it, right? Like it's 100% empirical. These are demonstrated on particular data sets for particular tasks. Now, it turns out that like as we're going to get to today, hopefully really soon, that like these transformers, because of the way in which these are particularly like good general learners, again, because of this way that it just, a somewhat simple mechanism for mixing up all the information in these sequences or sets of things, that you can train really deep, really large networks to do very general types of tasks that can then be fine-tuned to do all kinds of related tasks. And again, we're going to talk about that today, but like one of the reasons why transformers are like the thing everybody's doing is simply because of that. Like convolutional networks like aren't these general purpose kind of function approximators like these things are right here. I mean, there are so many analogies where you could argue with me on that, but like basically this is just it's actually a fairly simple way of being able to have be able to train effectively these big high capacity models. And that's what it comes down to. And the other one you can train them in very general ways without needing labels. And that's what we're going to talk about today. We're going to talk about how we train these things. So self-supervision to train on like massive amounts of data that doesn't necessarily have to be a particular like special task. And then you can fine-tune them on special tasks where you only have a little bit of data, and they tend to be state-of-the-art performers in that case. So again, that's the purpose of today, is kind of talk about all of that and show you like kind of like how it's done. But in the end, it's all because it works. And if something else worked better, your fault for making me talk forever. If something else had, if somebody else had come up with like something, I don't know, called like cool formers or something like that, and it was something different, and it was first, like that's what we'd be talking about today. We wouldn't be talking about transformers. And there's probably something even better than transformers that's coming next, but it's not quite there yet, you know what I mean? Like, or at least, we're not all using it yet. So it's a super, super empirical field. But I did try to, point out last time, this is really important, was to notice like how the elements of this, even though we added in, like we have this kind of weird attention thing, how a lot of the elements that are used in this are from previous models where they solved problems along the way, right? Normalization, skip connections, what else did I say? There's like one more and I can't think of what it is right now. Actually, I have no idea. Maybe it was only two. But there's another one. I'll think like halfway through the lecture I'll remember and I'll yell it out. But anyways, it's just I guess the other one is just attention, like how attention itself, the reason why it even shows up here is that it was shown to be very effective for long-range interactions in the recurrent neural networks. And so we just make a whole network out of those actions. Anyways, the point is that there is a kind of trajectory to this. It's not just like a fully random walk. It's a random walk with bias towards the things that are working. You know? Okay, wasted too much time on all of that good stuff. Let's move on here. So we talked about transformers. We talked about transformers as neural machine translation, where we have encoders and decoders, and the task is very similar to what we did with the recurrent neural networks, and that is to encode a sentence in like English and then translate it to French. So the encoder's about doing the encoding of the English sentence, or I guess in this case it's the French sentence, and then the decoding is about turning that into the other language, in this case English. And we talked briefly about this as well. This is just part of the architecture. When you have these encoders or when you have these decoders where you're trying to generate a sentence, just like we were doing with the recurrent neural networks, they're naturally autoregressive, so they kind of like, you're forced to sort of have everything conditioned on what's come before. Because these things are like set to set, they start off without any other intervention, being like, for instance, allowing the encode, or in this case the decoding of a token to depend on everything in the sequence, not just the things before it. So we had to when we were decoding, we had to put in this additional constraint that even though there is this information that we could have made use of, we set the attention values here to 0 so that we don't pay attention to these things, so that we preserve this ability, or like we preserve this ability to generate in the way that we expect to get it, which is like one token to the next. But actually, you can have encoder transformers, you can have decoder transformers, and you can have encoder and decoder transformers. And we'll talk about all three of those today and how each one of those is trained. Yeah.
So for the decoder in language, sometimes like specifically like Spanish, you're saying you would say like an adjective like after the noun.
Right.
How doesn't the decoder, wouldn't it stop that from understanding? Because it would see, I guess, the previous thing. In the encoder, like in English, you would say like the green cat, but in Spanish it would be the cat green. Like how does that get?
Yeah. So think about it this way. All that information about like what the sentence is about is here in the encoder in the other language. The decoder is about, okay, I have all that like semantic content. Now I just need to decode it into like the proper grammar in the other language.
Okay.
So you're right. Like I think I know why you're asking that, because it's like, I don't know. Like I should have, like maybe I need to know that there's a noun first before I produce the adjective or something like that. So like that makes sense in the language where the adjectives follow, but not when they precede the noun. But all that information is already it should be in the encoder, and all this is doing is saying, conditioned on that encoding, decoded in this other language. So the information's already there. We just have to produce it. Like if we're going to do this in a generative way, where we want this thing to like literally generate text for us, we can't have it generate text for text that hasn't yet generated. That's why we're I've said so many times like why you need to set this up. So yeah. Good question. Other questions? Is anybody feeling like really impressed with transformers, or is anybody just feeling like, wait, this is all it is? Like, is anybody not impressed? You can raise your hand. Oh, is that it, right? Raise your hand. Oh no, okay. It's kind of weird, right? Because it's like, and we call it AI. Like this isn't AI, right? Like this is just like some crazy way of putting together models that allow you to have a whole bunch of weights. It's just like really fancy data analysis. But if you call it AI, then you can raise a couple $100 million in your business, and that's good for you. Hopefully, good for your investors too. Okay, so a couple more things to talk about here as we get going on today. So we're gonna talk about how transformers are trained for basically language tasks, and they're used for many other things as well. But like this is a good it's a good prototypical example. So remember how we talked about blue scores for like natural or for translation tasks, right? Like we talked about how like what that's like. Well, when we're doing natural language processing and understanding in general, we translation might be one of the things we care about, but there's a whole host of things that we care about in general and using modeling for for natural language tasks. And so we need ways of evaluating that. And one of the sets of metrics that's kind of stuck is what's called GLUE, and there's actually additional versions of this, cleverly named things like super glue. But GLUE stands for General Language Understanding Evaluation, and literally it's just a collection of individual tasks, data sets and tasks on which to evaluate a general purpose language model. So we'll get into more of like what these are. It kind of says something about it here, but there's just a whole bunch of different tasks. And so when we're now moving into like more general language models, we need more general ways of evaluating the performance, and task collections like GLUE are the things that we're going to use to do these evaluations. Again, like there's a slide a little bit later on where we actually, I'll say a bit more about what each of these are, but you can kind of see some of these, like sentiment analysis, comparing sentences, paraphrasing, doing some question answering, some natural language inference, things like that. Okay, all right, so kind of a reminder. I've talked a bunch about the fact that you could do these, like, when you have your, both for the recurrent neural networks and for the transformers, you can't just give the text, like the word in text format as input. You need to encode it somehow. And we talked about one-hot encodings, which makes some sense until there's a huge vocabulary. And so then you might do some of these things that you might use as an initial encoder, something like word-to-vec or glove, which are just kind of pre-trained to learn representations that somehow have to do with like the statistics of just English language. Most of these things are what are called context-free, in the sense that when we encode these things, we do this kind of pre-training without there being like the context. When we do the encoding, we don't take into account the context of like surrounding the word. So like, there are many words like bank that have, for example, many words like bank that have multiple meanings, but when we do a context-free embedding of it, we're only going to, it's going to have one embedding. So whether it means bank like money in the bank, or bank like the edge of a river, like it's going to be encoded to the same place in this initial vector space. So that's probably pretty problematic if you want like a really powerful language model. So one of the important things about transformers is this way that it's creating embeddings of our tokens, of our words, that takes into account the full context. And it does this many times as it goes through the various layers of the transformer. But they're very simple kind of like statistical language tasks that you use to train like context-free encoder like word-to-vec or glove. How do you do that in general for these contextualized word embeddings? And that's, again, we're basically asking how do we train transformers in general. And we're going to be talking about a couple different examples as we go through here. Somehow, the first paper that came out on this had a Sesame Street name, and now there's lots of Sesame Street names. And it's like, maybe it's kind of dying out now because it's been a few years, but a lot of stuff got named after Sesame Street characters. But they were just, to begin with, they were just kind of fortunate acronyms. But then then you just kind of you force the acronyms to be a Sesame Street character. But we'll be talking, we'll be talking about a couple different kinds of transformers today, going by names like Elmo, GPT, which is, to my knowledge, not a Sesame Street character, Bert, and some variants of that. Okay, so the prototypical language modeling task that we've talked about is this idea of produce like the correct next word, and you can think of it as being conditioned on all the words that have come before it. Okay, and this makes a lot of sense. Why does this? By the way, I know there's at least one. Yeah, there's a couple of Last Airbender fans here, so good. I remember that there's a T-shirt one once. So, anyways, if you don't know the name here, then you just need to go watch some Nickelodeon. But so the idea here is that we have these massive transformers, lots of parameters. We need lots of data to train them on. If we're always going to require labeled data, we are in big trouble because we can't label that much data. Like think about all the work that went into labeling something like ImageNet that had tens of millions of images. We're now talking about needing billions and billions of data points. So the nice thing about language is doing language modeling is that there is a lot of in most languages there's a lot of existing examples of writing in that language, and most of it being digitized. So we're in good shape if all we need to do is just use, like if we can train these things to do general types of tasks without requiring anything else other than just like the fact that these are like real English sentences or whatever language you would be thinking about. So that's why we often focus on this, like something like this task right here, which is predict the next word. It's very natural. It's very much like, and it has this self-supervised characteristic to it, which is I don't need any more data than the sentences. I just need to know, if I have a proper English sentence, then I can just say, okay, from the first token, predict the second one, from the first two, predict the third, from the first three, predict the fourth, and so forth. Very natural, easy to do, no additional setup, lots and lots of data. But then what have I learned to do here? Well, I learned to do this task, but have I learned anything deeper? Like what information content is there in like the representations or the embeddings of these words that are coming out of my transformer? Like what kinds of this is like a rhetorical question. I'm not asking. You might have some really deep understanding here, but like what would we expect to have been learned by by tasks like this? Well, clearly it has to learn something about being English language sentences, right? It has to know something about, like, eventually it's going to learn just without it actually knowing anything about it. It'll learn something about parts of speech and the way that the grammar is formed and the way that like certain words follow other ones, and even for these long range interactions, how to kind of produce many tokens that maintain a kind of semantic content, meaning like if we're talking about a person or a thing, that like as we produce more and more text, like we see more and more things that sort of like make sense with regard to that person or that thing, and we can get into even more like nuance here. Like when you think about style, there's while it might be hard to kind of describe, there's definitely the way that you might write a thing down, or I might write a thing down, or a famous author might write a thing down, might have characteristics to it that are that are kind of like fingerprint for that particular person, and somehow that's all encoded in the way that tokens follow each other. The way you write it, the way I write it, in general, how we all write it in English. There's like general rules and there's like specifics, and so you might expect that by doing it, just learning a task like this, that the way, like the information that it's learned to extract from this whole, from all of English, and then and then encode the relevant bits of it for each of these tokens might be powerful for a lot of different tasks, and it ends up that it is that way. And how do we get at that? Well, we think about training. I've mentioned these words, but we're going to get more specific about it. We think about training now as having two phases, two stages to it. We pre-train on just, with these self-supervised tasks. So we don't need to do any labeling. We just collect up all the data we can possibly, put together. And we do these sort of simple but very general tasks. That will have learned, it will have learned something about, how to represent each of these tokens in context to, to be meaningful, at least to do that task. But we expect it to be, we hope that it's good for, many other tasks. And what do we mean by that? Well, let's say that we don't care about, producing the next word in the sentence. Let's say we actually want to take the whole sentence and do something like what we've talked about before, just kind of what seemed like a simple task, at least in terms of like setting it up, of saying, the sentiment that's being expressed in the sentence. One of the tasks that exists in Glue is this collection of movie reviews. When I look at this sentence, is it saying something positive about the movie? Is it saying something negative about the movie? Is it saying something neutral about it? So, literally what we do is we take these things that are pre-trained on this general task, and then we say, okay, let's now train it a little more. But what we'll do this time is instead of the everything being supervised here by the objective for this task, well, usually what we'll do is we'll actually freeze. Oftentimes we'll freeze the weights in this so that it's acting just like a very strong encoder. I mean, no, it says decoder, but as a way of producing embeddings of these tokens, and from that produce a prediction about the sentiment of this sentence. And often what happens is literally what happens for something like this, where we want to kind of go from that task to like a classification task like this, is we add an additional token here. So its weights, so additional token, so there will be some additional weights that show up now in the transformer, and then we'll have some like linear layers here for processing the encoding of this, what we often call a class token, for encoding that, and then giving us like the right dimensionality for doing our softmax layer for then applying cross entropy. So all it's the using of the weights for the bulk of this transformer, where we've already pre-trained it, where or by doing that, what we're saying is like we expect the way that it extracts information from this to be very good for these kinds of tasks. And it turns out that if you train on enough data with these general tasks, it ends up being that way. In fact, you end up getting state-of-the-art performance on these kinds of fine-tuned tasks, like the things that we saw in Glue. Why would it be state-of-the-art? The point is that the data sets associated with these like particular tasks are often very small, right? You're maybe talking about tens of thousands of sentences that have these labels on them. But language is really complex. So you're going to see enough complexity in 10,000 examples or 100,000 examples to really learn a good representation of that sentence, so that you can do this task as well as possible. The answer is probably no, just because of the great variety of just ways you can produce English sentences. But this thing, maybe it's seen all of the ways, not all of them, but it's seen certainly a lot more ways of producing English sentences, and has learned to kind of represent that more generally. More generally in the sense that there's all kinds of information that's been extracted from this sentence already to do that task, but in general to do a lot of tasks, and we just need to fine tune this so that we just get the information out of those representations that we need to do the task. And so we benefit from, you know, all this like general learning to do the specific task on a small set of data. And it works incredibly well. We're going to see, you know, we'll see examples. This is, I think I'm going to skip over this because I'm kind of going a little bit slow. This is saying just like more like in a mathy way what I was just saying. Pre-training with some loss gets us to a set of weights shown there by theta hat that are really good for general tasks. The fine-tuning starts essentially at that good set of weights for the network, and then does a little more learning, basically starting close to this set of weights. So the expectation is that like these weights right here are really good, and that we probably couldn't have got to that set of weights using just the particular task with that small set of data. So the pre-training on the big data sets gets us to a good place on our loss surface, you know, a good set of weights for the network, and then that gives us a good starting point for doing the fine tuning. And there's more words there, but that's essentially the idea. Okay. So, like I said, or I mentioned this a little bit earlier today, but when transformers were introduced, they were introduced in the context of natural language or these neural machine translations, doing well on those kinds of tasks. And so the way that the way that the architecture was expressed, looked like this encoder decoder transformer. But there's really nothing like intrinsic about like in general. Both these parts are not necessarily needed for the task that you might be interested in. They are, when you're doing this kind of sequence to sequence, like this makes a lot of sense, but we may only care about having decoders, basically things that can generate text, or we might only care about encoders, where what we want to do is just learn very general representations of our language, and not necessarily have these two things put together. So that just kind of depends on the task and what you're interested in doing. Are you interested in generating text? Are you interested in getting the best representations? Are you interested in doing this sequence-to-sequence translation? Each one of those, if you think about this in the context of the pre-training and fine-tuning, each one of these needs to be pre-trained in a slightly different way. That's what we're going to talk about next. We've been kind of referring to this already, and it'll look familiar, but this will be quite different. And again, what's the difference between decoders and encoders? Decoders for language, only when you're decoding it only gives you access to the tokens that have come before. With encoders, you get access to all of the tokens. So that kind of determines, again, which of these you would use is determined by the task. So let's talk about the decoders. This is basically this repeat of everything we've said up to this point. You pre-train them usually on this task of predicting the next token from the previous tokens, and then you sort of add this additional, whatever the task is you want to do, sort of you slightly adjust your transformer so that there's something that can learn to do the task that you care about. And then this just looks like everything that we've done before. If you say if this is a classification task, like in the sentiment analysis, you just kind of add the right machinery there, and then you do the fine tuning. I've said this a couple times in this class, and these are just like this example kind of just reminds me of it, and I just want to bring it up again. One of the nicest things about working with neural networks, besides them working so well if you have a lot of data, is that they really are like the best, coolest set of Legos you could have bought, or got for your birthday or something, when you were a kid. Like, I never got one of these. I'm the oldest in my family, and I just grew up when my family didn't have any money, so I always wanted that huge box of the general Legos, you know, because it seemed like I could have built, I don't know, a spaceship or something to do, or just something really cool instead of just like, I don't know, a dumb little house. But and you know, like, you know, things like you know, things like so like support vector machines, things like random forest, and so, even though these are like really powerful, in some sense these are like dumb little houses. Like you get that dumb little house kit, and you can only build that. You can only build that thing. You know, once you start doing neural networks, you basically like you can kind of make as long as there's always a differentiable operation that, you know, to kind of approximate, or that is or that approximates the thing you're trying to do. You can just put these things together in all kinds of crazy wild ways, following on what's, you know, like best practices that have been learned for putting those architectures together, and you can make kind of whatever you want work. And it does, you know, it does, even though like it seems like it's not constrained in some ways, of like, wow, like, you know, how do they choose those architectures? It does in many ways, you know, have a set of constraints that allows you just to do a lot of different exciting things. And so this idea of fine tuning is definitely one of those. Anyways, because I feel like a little bit behind, I'm going to keep going through these. This is mostly saying everything. This is saying over and over again the kinds of things I've already said. Let's talk about some examples. So we're talking about just decoder only transformers. GPT. So GPT-3 kind of made the GPT family of models really famous. But there was, you know, before there was a GPT-3, there was a GPT-2 and a GPT-1. Although, you know, we don't say the one. There was GPT, and actually, it turns out that like GPT was written, like the acronym is in this paper from 2018, but like what the acronym actually means wasn't actually in the paper. So it's like no one really talks about it as a generative pre-trained transformers. Maybe it stood for something else, like generative pre-training or something, but we just call them GPT. This came out from OpenAI, and it was like a really, really kind of like this, like first in a series of really powerful decoder transformers. So what did this look like? So we just have the decoder part. What that means is that we don't have the, you know, because we don't have the encoder part, we don't have this like conditioning head where we condition the spatial, or sorry, the self-attention, or the attention on the encoding tokens. We just have, you know, we just have the single self-attention head, but that is masked so that we can't look at tokens that are ahead of us in the sentence. Okay, so what does this look like? So think of that, just that decoder, but having 12 layers. The hidden states, so like basically like the token, or sorry, not the token, but like the sizes of the embeddings within each layer were 768. I don't have a good sense of why that particular number. For the self-attention layers, and then this feed-forward layer where you expand the dimension and then contract it back again, that was 3,000. Had dimension 3072. So again, it's like this expansion feed-forward layer. Instead of using like word2vec or glove, or certainly not, you know, one-hot encodings, this used byte pair encoding of words. Anybody seen or heard of byte pair before? What that looks like? It's basically a way of like looking at like common patterns, like the most common patterns in like characters, for instance, in a word, and then replacing those like pairs of, like, think about like characters that follow each other, replacing those two characters that follow each other, like that appear the most, and replacing that with like a different character. So like you're getting rid of your this double character for a single character, and then you kind of just iterate this. Those are called merges. This was done 40,000 times over the like the corpus, and this gives you a way to represent basically what you end up with, and this is why it's called byte, is that so the pair is coming from these merges of the characters, but this byte is that you end up with an integer. It's like, think of it as kind of like a hash, but it's an integer representation of that particular word. And this is actually how like most transformer encodings kind of look like these days. If you were to read a paper, you'd almost see, it might even skip over this now and not even talk about byte pair encoding, but if it doesn't, then you can assume that it's actually using this kind of encoding of the text. It's a very powerful, like very efficient way of encoding these strings of characters as integers. So then, okay, so now your vocabulary is just like all these integers in the, with just this list of integers. And then this initial GPT was trained on what's called the books corpus. So some 7,000 plus books, and when training, you have to you're wanting to do this like in the decoder. You're trying to do this next word prediction task, but how long a sequence you want to do that over is kind of up to you. And so this was done in such a way that we had like the input was often very, very long, excerpts from these books to be able to learn very long distance dependencies. I wish I had it on here. I don't recall the number, but it's long. It's something like 10,000 tokens or something like that long. Yeah, and then this thing about the acronym never showing up. So this was GPT. It learned to do this task. Let's see. Do I have on the next one? Yeah. Okay. It learned to do this general task. Now, what were the fine-tuning tasks? So, there's a bunch of these we already kind of we've talked about, or like they're pretty obvious what they are. So like sentiment analysis, question answering, those kinds of things. But there's a lot of tasks that are called natural language inference that we want to do this kind of fine-tuning on. What are those? So what the task is that you're given two sentences, what are referred to as the premise and the hypothesis. So in this, we have this example of a premise: the man is in the doorway. Hypothesis: the person is near the door. So the thing that you're trying to do is you're trying to get this sort of logical inference where you're saying, does the hypothesis follow, or is it entailed by the premise? This, this is, if it's not entailed, it might be contradictory, right? So like the two don't, like this can't possibly follow from the premise. Or it's neutral in the sense that like neither one entails the other. This is an interesting task. If you can do this kind of task really well, it sort of feels like you learn something, like to reason about the contents of a sentence, right? And to think about like how, I don't know, like how people and doorways relate to each other, like how this particular relationship might like entail or contradict this one right here. So there's a bunch of these natural language inference tasks, like in Glue and the other kinds of tasks. So so in this work, it turns out that like GPT ended up doing very, very well on this task. Now the thing you might be wondering is, how do I decide this if all I have is a decoder, right? If all I have is, just like I can just produce this, or I can just like encode the sequence of these, this whole sequence here, but only one token after the other. And the way that you do that is that you put special tokens into this. So you basically just you're saying, here's the start of the two, I guess basically of the first, like the premise, then some sort of delimiter saying like we're ending the premise and starting the hypothesis, and then that we're ending the hypothesis, and now we need to do the Now we need to do this, like basically this classification task from the fact that we see this extract token here. So when this token applies, or when this token appears, that's when we do the classification task. So in the paper from 2018, they show that, and this is like the most common format for all machine learning papers, is that you have your tasks, you have all the other methods that came before you, and you somehow you're way better, and that's shown by the bold numbers here. Every single machine learning paper has a table like this. Well, almost all papers have this. So, and you can see there's actually one example here for one of the tasks where these models here are actually better. But in general, these were better and a lot better, looking at some of these numbers. So anyways, a lot of these are, again, these natural language inference tasks. And actually, I think all these are the natural language inference tasks. And it basically, it's done really, really well on them. Now, importantly, some of these networks were trained just to do this one task. Remember that, like, for each of these, what you have is a pre-trained GPT model, and then fine-tuned for each one of these tasks on the particular task data set. So an example of the kind of thing I'm talking about, which is when training large models on these general tasks and then fine-tuning them, you can often just find yourself with state-of-the-art performance. And the story that we'll see here as we kind of keep going is the bigger these transformers get, and the more pre-training we do on them, the better we end up doing when we transfer and fine-tune to these other tasks.
So are they pre-trained on each one of these data sets?
Yep. Yeah. So it's like there's like one parent model, like the pre-trained model, and then there's like a child model for each of these. Like I train one of these to do this task, and then I train another one to do this task, and so forth. That makes sense? Yeah. Okay. So GPT-2 is basically, like I just said, it's the same story, kind of trained in the same way. It's just bigger, trained on more data. And what's cool about this is that it started to the kind of the text that was being generated from these models I guess you'd say got people's attention. It started to look a lot like what an actual human might write. So the way that these things work is that you often, what you'll do is you'll seed these things, right, with a certain, what we often call the context, but just like a certain amount of text, right? So this is a generative model. So you're going to just give it this and say, here's the beginning of the text that you're going to generate. Now generate, token by token from here on out. So, this is kind of cool to read, right? And again, these are cherry-picked examples, and we don't have time to go through all the cool examples, but, let's just read this real quick and we'll kind of see what I mean. So, here's the context that's provided by a human. In a shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley in the Andes Mountains. Even more surprising to the researchers was the fact that the unicorns spoke perfect English. So, one of the things to remember about this is that the reason for giving this this kind of weird context is that one of the criticisms that you could level at these massive models learning to do these these very general tasks is that they're so big is that they're memorizing all of the training data they ever saw, and that the weights are just a way of kind of reproducing that training data when the right context appears. But if you give it kind of a bizarre context like this, I mean, yes, it's almost certainly, seen stuff about unicorns before, right? Like, even though they don't exist, or at least I don't think they exist, but maybe they exist. And that they don't, they certainly they don't speak English, and they certainly haven't been found in the Andes Mountains. It's not like it's seen text like this before, and it's like, I'll just spit out the text that's like closest to this, because it hasn't existed before, it hasn't seen it before. So what does it now produce, token by token here? So it says, the scientist named the population after their distinctive horn, Ovid's unicorn. So already, like, that's really clever. Like, it's created something. Ovid's not like it probably saw a name like Ovid before, but it's it not only like kind of did this neat little like creation of a fact that of course doesn't exist. It did it in a way that sounds kind of like the way that this sounds up here, which is like, reporting on a scientific finding, right? Like this sounds like what you would write if you were to report on a scientific finding. So it's not only producing something that's kind of like creative and semantically kind of correct, it's also doing it in an appropriate style. And this really caught everybody's attention. Like, wow, how's it doing this? These four horns, silver white unicorns. So all of a sudden you have four horns. I don't know. Silver white unicorns were previously unknown to science. Now, after almost 2 centuries, the mystery of what sparked this odd phenomenon is finally solved. So you start to kind of lose a little bit of coherence here, right? Like, this sounds like we just discovered it. This sounds like, well, the unicorns, we've known about them for years, but now we know something new about them. So starting to lose some coherence here, but it still sounds, again, like it's still in the right style, and it's still, is talking about the right kinds of things. Notice this next sentence. I think this is quite cool. Dr. Jorge Perez, I probably didn't say that right, an evolutionary biologist from the University of La Paz, and several companions were exploring the Andes Mountains when they found a small valley with no other animals or humans. Perez noticed that the valley had what appeared to be a natural fountain surrounded by 2 peaks of rock and silver snow. So notice that, notice a couple things. One is, some of the content, some of the semantic content is preserved. We're talking about La Paz, we have a Spanish name that fits in with the location in which this was this context was given. But we really lost the thread on the unicorns all of a sudden, right? Like all of a sudden, we're not talking about unicorns anymore. We're we're in a valley, which makes sense because we're talking about mountains. We're talking about mountains, so there's snow, there's fountains. So if you're reading this, you go, wait, this is really bad reporting. I wanted to learn about the unicorns, and there are no more unicorns. You're telling me about just dumb details I don't care about, which is right. So this thing isn't perfect in the sense that it didn't produce the kind of text that we would have hoped it could have done, but it really is way better than anything that kind of came before it in its ability to do this. And again, the reasoning for this is this ability, these massive models trained on massive data to do this text generation task. Okay, we're going to come back to decoders in a bit because we'll talk about GPT-3 at the end of this. Okay, encoders. All right, so again, decoders is kind of like the canonical example because just like the task of producing or predicting the next token is sort of I don't know, just sort of obvious, sort of makes sense. What's not obvious is in this case. So let's say we just want amazing, embeddings of or representations of our tokens within the context of a whole sentence, and we don't care that we need to sort of decode this in sequence. We just want we want to use the whole of the sentence or the whole of the document that we're going to input into this thing to be able to shape that token representation. And that's what an encoder is about. So what's weird about that then is well, what's the right task? Because you can't go do this task now. Because this task is about, you could do this task, but it would have access to the word itself that it needs to predict. So we just look at that and say, it would learn, give me this next one. So that kind of task doesn't make any sense. It wouldn't learn anything useful. So how do you, in this case, train something, you know, that will learn really useful general embeddings? Well, it's not that different from what we came before. We just have to be a little bit more like clever about it, because we have to kind of decide, well, what is it from the sentence that we want to predict? Remember, one of the criteria here that we are trying to meet when doing this pre-training is that we just want to do it in a self-supervised way, meaning we don't want to have any labels. We just want to be able to use the text itself and train generally. So this is where BERT comes in, and BERT stands for bidirectional encoder representations from transformers. So there was already an Elmo, so the bidirectional comes from the fact that like we're no longer doing the decoding part where we're masking out everything before. We're allowing context from both sides, for all the tokens, both sides of a particular token within the sentence. So that's the bidirectional part. And then we think of these as as encoders in that case, because we're not using this in a decoding or a generative way. So how do you do this? Well, BERT proposed an objective that is still, it's used widely and has been adapted to all different kinds of data sets that not just language, but other kinds of data sets, for instance, like representations of molecules. Like a colleague and I just put up a paper on Archive today about one of these ways of doing it. But anyways, for molecules. But the point is that the objective here was something called masked LM, or masked language modeling. And it's a pretty simple idea. The idea is that you're going to have the whole sentence. So you want to predict something about this sentence. Well, what do? Well, the way that this was originally set up, and we mostly follow this this pattern still today, is that there's going to be some long sentence here. This is only 5 tokens, but usually going to be much longer. You're going to randomly choose 15% of those tokens. So if it's 100 tokens long, you're going to you're going to randomly choose 15 of those. It doesn't matter where it's going to randomly choose them uniformly. And from those 15 words in that case, those 15 tokens, we're going to take 80% of them, so 4/5 of them, and we're just going to mask them. Okay? We're going to add a token to our vocabulary, and it's going to be the token that just is like, it's kind of like the unknown that we saw before in the R9 when we were doing neural machine translation. And whenever there's a masked token there, what we're going to want to do is actually predict the word that was there that we masked. Okay, so we're going to build up an objective here, and so we're going to take out of our 100 words in the input, we're going to take 15 of them, 15 of them, 80%, so 12 of them, we are going to mask, and then we're going to force ourselves to predict that correct masked token. 10%, so 1.5, so whatever, we might round it to 1 or 2 or whatever. We're going to take those, and we're going to instead of using a masked token, we're just going to like randomly put some other token in our vocabulary in there. So kind of like add some noise. So like this adds some noise in the sense that like we're removing information. This adds some noise in the sense that we're like putting in disinformation. But it's a very, very small number of the tokens that this happens to. And then there are going to be, and again, we're going to want to predict the correct word. So again, when we do this, when we like replace this with some random word, we now add this to the objective. We need to predict the correct one. So that was went, but we put in pizza. So we need to predict went, despite the fact that pizza is here and is going to be part of the encoding. And then the other 10% of that 15%, we're not going to do anything to it, but we still want to predict it. So we're going to leave the token as is, but we're going to force ourselves to predict it, which maybe seems kind of weird because, well, the answer is there already. But the point is that like it doesn't know if it was one of these that was wrong. It has to be correctly decoded, or if it's one of these that is right. And it turns out that like through some experimentation, the authors on this paper through some experimentation found that like they needed to do this because otherwise the model just learns to really focus, only encode the masked or the mixed up words and not just like the rest of the tokens themselves. Just kind of an interesting fact here. So that's the task. The task is we're gonna corrupt this sentence, and then we're gonna correct it. We're gonna correct the corrupted sentence. And there's two kinds of corruptions, and then one like thing that's not a corruption, which basically you're forcing the model to figure out when it's not a corruption. Okay, so questions on that? Does that make sense? This is actually really, really important. This is like the crux idea, for pre-training these things. So there's the generative, like predict the next token. But if we're not doing that task, then this is basically the other task that we do self-supervised training with.
For pre-training decoders, we have the paradigm of like the pre-trained thing exists, and then we have on top, how does this change that?
Yeah. So you mean like the fine-tuning?
Yeah. Sorry.
Yeah. Exactly. We're going to do fine-tuning here.
Okay.
Yeah. It's going to look exactly the same, actually. It's just that it'll only be for tasks that aren't these generative tasks. Like, we can do the sentiment analysis tasks. In fact, these things are far better on the glue tasks because they're taking into account the whole of the sentence, whereas the decoders aren't doing that. They still do really well. They still are state of the art, but like at least at that time. But these come along, a year later, and they're better. And again, the reason is, the pre-training task is different, but really it's that when you're encoding each of the tokens, you take into account the full sentence rather than just what's come before the token. All right. Any more questions on that? Probably have lots of questions, but so I said that was the most important self-supervised pre-training task. Actually, when BERT was proposed in that paper, they actually have a separate task where they are where it's basically like it's a form of this entailment where they also trained it to take in one sentence. You again have these special tokens that kind of tell you like where the first sentence is and where the second is, and the task is to say whether or not the second sentence follows or is entailed by the first. Most later work after this kind of showed that this was not necessary. It didn't help the representation, and people don't train it. They just do the masked language modeling task. These models are starting to get larger, so you will see this, when you go to your model zoos. So Hugging Face for PyTorch is the transformer library, and you'll find in there different kinds of birds, but you'll find a BERT base and a BERT large, and it'll basically have these dimensions. The architecture will look like this. So 12 layers or 24 layers, the size of the hidden states, how many attention heads per layer, and then just total number of parameters. So these are getting larger and larger, not to the billions yet. Trained on much larger corpuses, and turns out that for such huge text and such huge models, this required quite a bit of training. Still not as impressive as GPT-3, not even close actually, but a lot of training. And then the same thing's going to apply. We pre-train these things and then fine-tune to whatever task we care about. And then here are those entailment tasks, and you can see that we have GPT. Remember, we saw these numbers from before. Here's BERT base and here's BERT large, and again, whenever these tables show up, just expect to see all the bold numbers at the bottom. That's how this is. If a transformer learned to produce a machine learning paper, it would produce tables like this, with bold numbers on the bottom, hopefully larger than the rest. I'm starting to run out of time, I guess, because we have only got a couple minutes left. But I had mentioned, these are descriptions of the kinds of of the glue tasks. So things like paraphrasing, things like the natural language inference, things like sentiment analysis, question answering, and then this is kind of an interesting one, whether or not a sentence is grammatical. So like, that's like a binary classifier. Is it following the rules of grammar or not? And then more inference tasks. So now we have a new, we had 2017 we had a new winner on these tasks. Then 2018 we have Berton large. It's it's better. Great. So let's see. I just want to make sure. Can't remember. Oh yeah. Okay. So you might say like, this is great. I am like, maybe that's all I ever need to do is to train these encoders. But what this is saying right here is just it does not lead to that natural autoregressive learning that you need to produce one token after the other. So we have to have a variety of these different kinds of models. There have been modifications to BERT since then. Roberta, SpanBERT. These are things just like we make the models bigger. Sometimes we change the tasks. So Roberta was basically just like BERT v2. It was just like we get rid of that sentence entailment thing, and we just bigger, train it for longer. SpanBERT is this thing where when you're doing the masking, sometimes there's kind of random choosing, but oftentimes what you want to do is instead of just the mask showing up kind of randomly uniformly through the sentence, you want to put these things together, making this task even harder. Because if you think about what's happening when you're masking these things, it's trying to figure out what word goes there from all the rest of the context. And usually the words that are nearest by will give you the most context for how to do, for what word should have been there. And of course, this just makes the task harder if all these masking are like sequential. So just kind of making the task harder so that it's learning more about the language. And guess what? Roberta does better. Bold numbers in the final line there. Okay, and then we talked a lot about encoders and decoders. This is mostly for like the sequence-to-sequence kind of tasks, like translation. But you could do this for question answering and anything that kind of has this natural what you want to do with this sentence needs to be somehow or this this set of tokens needs to be conditioned on something fixed, like the sentence you're translating. These can be pre-trained as well. The famous example here is T5 from Facebook. This stands for text-to-text. Oh, shoot. Text-to-text something transformer. I can't remember. A lot of T's, 5 T's. The way that so if you're not doing a translation task, you could still pre-train this. And the way that they do this is your input removes a bunch of parts of the sentence or masks them, and on the other side, you sort of do the inverse. You mask the things you didn't mask here, and you basically want it to learn to produce the entire sentence. So you're training with this, masking with this. You kind of get this conditioning across the two sentences. Not very often are you going to find an encoder decoder being your general pre-trained model for then fine-tuning. These are mostly reserved for these sequence-to-sequence tasks. They clearly didn't know how to write a machine learning paper. They put the best model up top. Okay, so just with the couple minutes that we have left, just 2 or 3, I just want to talk about GPT-3. Okay, so we're talking about models that were in the hundreds of millions of parameters, and then we start to get into like the low billions. I kind of skipped past this T5 model, but it had 11 billion parameters, so it's starting to learn more and more. So now, 2 years ago, GPT-3 comes out, this third transformer in this family. It's still a decoder transformer, but it's now huge. It now has 175 billion parameters. So we keep going up in orders of magnitude in terms of numbers of parameters. And what's interesting about GPT-3 is that it does everything that GPT-2 could do, but better, because somehow we're in this kind of interesting phase where the more we scale up, both with size of the networks, the capacity of the networks, and the data that we have to train on it, like it's like we just keep getting better and better results. What's really interesting with GPT-3 is that you start to get what appear like certain kinds of emergent behaviors, including like things that we would call few-shot learning, or like learning that doesn't require like a kind of fine-tuning, if you want to think of it that way, that doesn't require there being any kind of gradient steps or this gradient descent learning. And what do we mean by that? It's this. So we did all this pre-training exactly in the ways that we've been talking about, just with much bigger models, with a much bigger model with way more data. And then you could do things like this, where you give it some examples, just like this, like literally this is the context. And you can go do this because the GPT-3 API, you can get access to it and play around with it. You can give it this, and then you can give it 5 plus 9 equals, and it will produce 14. Or you can just give it this, and it'll just produce this pattern over and over and over again. And it does this for all kinds of these very simple patterns. So this is like a translation pattern here. This is like a spell correction pattern. And literally, this is the context. Again, the thing it'll produce as it starts to generate from this context is examples of this, of doing this. Or what's even cooler, right, is you could give this some word that was misspelled, give it this token, and then the thing it'll produce next is, in general, it will be the properly spelled version of that word. So if you think about that, that's really interesting. You probably never saw an example of thanks with this, bold arrow and then merci after it, right? You probably didn't see that. I mean, you can imagine that maybe there was some text like that, but in general, it probably didn't see that. It's just learned to produce one token after the other. One token after the other. But it's got this capability of being able to just infer deeply what the pattern is here in just a couple of examples. And there's no fine tuning involved. No fine tuning at all. And you can play around with this yourself, and it's pretty amazing. We looked at some of these examples at the beginning of class, like the first day of class. Oh shoot, we have that thing happening again. But again, you could give an example, some context where it's content, and in this case it's from Harry Potter, but in the style of a particular author, and this thing does an incredible job of producing text that both preserves the content and the style. So remember we talked about content and style in the computer vision context. We saw that we had ways that where we could learn one from the other and give it examples of the two different things, and then it would combine them. Here you're not even telling you're doing sort of the same thing, but you're not separating those things out for the as distinct inputs for the network to do this with. This is just all at once an example of it, and it sort of can figure that out. It can understand that content and style distinction and produce text accordingly. And I don't know, we can go through these examples. One of the coolest things here is people built question answering systems, and literally this is whatever this question is, that is just fed as context to the GPT-3, and it will often give the correct answer. It's not perfect. There's many ways in which it fails, but very often it'll give the correct answer. And remember, it wasn't trained to do question answering. It just did token, predict the next token, generate text, produce HTML, all kinds of fun stuff. We looked at these already. Oh, there's a thing. All right, so that's where this got to. So everybody's anxiously awaiting GPT-4. Everybody's anxiously awaiting the next, big, what's the next biggest model? One of the things that's just to point out here is that as these models have gotten much, much bigger, they become way more expensive to train. The estimates of like the training cost for GPT-3, you know, who knows exactly, but most people are thinking that it costs about $12 million to train GPT-3. So there's so many interesting, and we'll probably talk about this at a different time when we have some more time and some flexibility in our schedule, but we'll talk about like what that means, you know, for, you know, just the, like what it is that, like who has access to the power of these models, and you know how that's how that is really intertwined with just the reality of the economics of like how expensive it is to train these things. There's been some really interesting developments. It turns out like people are touting, hey, I can train GPT-3 and it only costs $500,000. And you know, and it's amazing that we're in this like situation where you know people in the know are like, only $500,000? That's amazing. That's cheap, you know. But you know, I don't have $500,000 to spend on, you know, doing this for fun. And so like, you know, who gets to build these? Who gets to use these? You know, all the questions about the bias that biases that get introduced into these kinds of models when they're trained on just like, you know, all the text from the internet, so to speak, and it's not curated in a way that maybe would remove certain kinds of like, you know, questionable content that you wouldn't want to be learned by, you know, models that just generate text. So lots of really interesting kind of socially, you know, societally important questions, but we won't do that today because we're way over time. Thanks for staying longer.